Hey there.
Good morning.
How are you?
Good.
Good. We'll give it a few minutes. Yeah, my population numbers in my classes earlier today were kind of low. Okay, good. All right. So before we get started, I just wanted to talk about the quiz. I graded the quiz for chapter quiz 3. It's chapter 2.2 on the basic matrices, and I just want to go over some stuff I noticed happened on the quizzes, and I want to talk about some of the stuff in particular. So on question 1 on the quizzes, let's see if I can get this straight. Question 1 on the quiz. So we got A, B, C, and D are all matrices. So let's write out our dimensions. So A is a 4x5 matrix, right? B is a 3x4 matrix. C is a 2x3 matrix, and D is a 3x4 matrix. Okay, so these are all the dimensions. Okay, so then you're asked to do like, you know, what would it be? Can you do these different types of procedures? So question A said, can we do D plus B times A? Okay, so the first thing I'm going to do, D plus B. So D and B have to be the same dimension. So 3x4 and 3x4. So D and B are the same dimension, which means when I add them, I'm going to get the same dimension. A now is a 4x5. So remember, we check our inner dimensions. If the inner dimensions agree, I can do the multiplication. My answer will be a 3x5. Okay, so that's part A. So part A is yes. Part B says, can I do D times C? So let's write out what we have. So D is a 3x4 and C is a 2x3. So watch out, order matters, right? I'm going to put them exactly. So D is 3x4, C is 2x3. I check my inner dimensions and, oh, they don't match. So no, I can't do that multiplication. C, part C says 3 times B minus 2 times D. So now this is a trick question. I saw some people get this part wrong. This is a scalar multiplied by B. So all I'm doing is I'm taking the number 3 and I'm multiplying it by every component inside B. So scalar multiplication. So 3 times B, so 3 times B will not change the dimensions of B. I think what I saw on some of the quizzes were that people thought 3 times B is going to make this a 9x12 matrix, which is not the case. All this is it's going to take the number 3 and it's going to multiply it by all the numbers in the first row, all the numbers in the second row, all the numbers in the third row, right? All it's doing is just scaling, right? Same thing with 2. So if I could do a D and a B, if I can add those, I can subtract the B and the D. So this is going to be ending up being a 3x4 minus a 3x4, which is a yes. I can absolutely do addition, subtraction on matrices that have the same dimension. Okay, that's part C. So part D said B times A. So B times A. So B is a 3x4 and A is a 4x5. I check my inner dimensions. They agree. And that means, yes, I can do my multiplication. My answer will be a 3x5 matrix. Okay. So be very careful. I think this one is the one that people got tripped up on, where they thought that was somehow changing the nature of the dimensions of the matrix. All you're doing is scaling every term of B by 3, and I'm going to scale every term of D by the number 2, and then I'm going to add those things together. It's the linear combination that we have been talking about. Okay. And I think you guys got 2 and 3 correctly, and then and I think you guys got question 4 correctly too. When you did it, I'll try to mention the insides. Seem to yeah, right. And Yeah, I saw that too. I think that people thought if they're gonna add these together, they're gonna try matching the insides. But the insides, we only have to worry about that when we're multiplying, right? And then dividing is a whole different ball of wax. It's like we're not covering division, matrix division in our class. Anyway, but multiplication, we check inner dimensions. Addition and subtraction, they just have to be the same dimension. Okay, so totally fine. Anyway, I'll post these solutions later so you guys can have them to study for the next midterm, which is coming up in on the 16th. So we're talking about not this week, not next week, but the Monday of the week after. The 16th is a Monday. So keep that in mind. We've got a midterm exam coming up. I've already posted, if you check one of them, the module, I think this week's module maybe, I'm trying to remember. I've got extra review materials for exam 2. You guys should be able to download those and take a look at that stuff. Okay. All right. Have I talked enough? All right, let me get out my colored pencils here. And we can keep talking. So last time on Monday, we were talking about quaternions. Very exciting, right? So quaternions are a way, we haven't learned it yet, but they're a way for us to be able to do a rotation in 3 dimensions. Excuse me, a rotation in 3 dimensions. And they help me avoid some of the problems that I have when I do rotations with angles, right? So if I'm in 3 dimensions and I want to rotate, some degrees around some object, right? I have to break that angle down into its X component, its Y component, Z component, and then, deal with all those different aspects of it. So I get this pretty big conglomerate, rotation matrix, which actually ends up being very computationally expensive. Quaternions sound really complex. They have this funny name. They've got like cross products and dot products and stuff, but those are all just multiplication and addition. It's pretty straightforward. So I don't have to worry so much about, doing a lot of heavy computations when I'm doing quaternions. So it seems like it's more complex, but it's actually not, and it's computationally cheaper. So we talked about quaternions last time. So where we left off last time was we were working through, I've got my lecture examples for chapter 2.7, part 1. We're on part 1. Part 1 is dealing with quaternions. Part 2 is dealing with what we call Euler angles. That's where we rotate the long way, where we have problems. But I'm teaching you both, and just so you know. Anyway, we were on example 3, and I stopped after doing the scalar portion of it because we have to do the cross product and then scalar multiplication. So remember, when I multiply 2 quaternions together, I should get a quaternion as an output. I'm going to get a scalar portion and a vector portion. Okay, to calculate the scalar portion on my quaternion multiplication, I just plain old multiply the 2 scalars together, and then I subtract out the dot product of the 2 vectors. It's like I'm going to get rid of the double counting. Okay. Now I have to deal with the vector part, which is I need to do a cross product, and then I have to do a couple of scalar multiplications. So let's go ahead and do our cross product. So I'm going to go P cross Q. So I'm doing this in different colors so we can follow through. Okay, so let's set this up. So P cross Q. So my I, J, K, my P, the vector portion of P was 1, minus 2, 1. The vector portion of Q was minus 1, 2, 3. Remember our cross products. I'm going to start working it through. This is equal to I times first row, first column. I ignore those. And then minus J, first row, second column. Ignore those. Plus K, first row, third column. And I build up what's left over. Okay, now I'm going to do my cross product. So I'm going to start working it over here, which is equal to I times minus 2 times 3 minus times 1 minus J. This is going to be 3 minus a minus 1 plus K. This is going to be 2 minus 1 times minus 2 is positive 2. So it's minus 2. So we're dealing with a vector that's, this is minus 6 minus 2. So this is minus 8. This is 3 plus 1. That's 4 times a minus 1, minus 4. Minus 2. 2 minus 2 is 0. Okay, so I'm dealing with, this is my vector that goes right here. P. So this is part one from here. Okay, now I'll do this in, I'm doing these all in different colors so we can follow it. That's, I'm going to add that to, oops, added to P naught times Q. This is a scalar multiplication. So P naught times Q. So P naught times Q bar. So P naught is right here, 3 times my Q vector, minus 1, 2, 3. It's got to be a vector because remember, we're dealing with the vector portion of things now, right? So I have a scalar portion and I have a vector portion, P naught times Q. And then I'm going to add that to Q naught times P. It looks like I'm doing that in black. I'm going to get my black pen. So I'm going to go Q naught times P. So Q naught was equal to 2. And then the P vector is 1 minus 2, 1. Okay, so let's add these together. So this is a minus 3, 6, 9. Plus, it's going to be 2 minus 4, 2. And then remember, this is minus 8, 4, 0. So I'm going to add all of these together, right, to get a vector out. So I'm going to add, so minus 8 minus 3 is minus 11. Minus 11 plus 2 is minus 9. 4 plus 6, that's 10. Minus 4 is 6. 0 plus 9 plus 2 is 11. Okay, don't forget your scalar part. Plus my scalar, 8. Okay, so this is our resulting quaternion. This is our answer. Right, this is the quaternion that results when I multiply the quaternion P times the quaternion Q. Okay, so I've got a quaternion P times a quaternion Q. I multiply them together, I get a quaternion as an answer. 8 plus minus 9, 6, 11, which I can also write as 8 minus 9, 6, 11. Okay, remember our quaternion has 4 elements to it. Okay. So far, so good, you guys? All right, all right, so what I'm going to do, I'm going to take a step back and I'm going to do some classwork problems. So I have classwork chapter 2.7 part 1, right? The first one is I'm going to multiply 2 quaternions together. So I'm going to put into practice exactly what we just did, right? And then I'm going to, question number 1, question number 2, we're multiplying 2 quaternions. Question number 3, we're adding quaternions. 4 and 5, these are all just, you know, looking at values, different things of quaternions. Then we do rotations with quaternions. So let's do these classwork. Isn't it minus 4 for the first one? Where are you looking at? Minus 4. Let me see. Did I write that down wrong? Oh, yes, there's a minus 4. Let me check. Did I write that down wrong? I think you are right. Let me check. Oops, I transcribed it wrong. Thank you. So let's do that again. So I've got, where am I? So 4. So 4. Okay, so minus 4 plus 6 gives me 2 times minus 4. This is going to give me minus 2. Thank you very much. Good catch. Then that's here. Be minus 2. Good. Thank you very much for catching that. I'll throw in these mistakes every now and then, see if you're paying attention. Alrighty. Okay. So let's take a step back. You guys have this here. And then let's do some practice on our classwork pages. I'll do it with the camera on with the recording. And then then we'll check our answers on stuff. I'll just work it through, and you guys can either watch it, do it on your own. You can check your answers if you want, and then we'll come back in about maybe 15 minutes or so, and we'll go back and talking about rotations using quaternions. Okay, so I'm going to start working through these things here. Yes, so I'm still having office hours today, and the class video for 2.6 should be posted on the modules page. I'll check it. I'll check it after class today. I believe I posted it like Monday. If it's not there, I'll go track it down and put it there. Maybe it's not published. I'll go check. I'll check it right after class today. Went from 2.5 to 2.7. Let me check. I'll check it. Let me track it down. Okay. Let's see. I know I have the lecture examples for 2.6, so I know we covered it. It may be possible that it I'll find it and I'll check it out. See where it is. I think on Monday we finished up chapter 2.6 also, so it's possible. We have a little bit Monday's lecture, which is mostly 2.7, but it's like the ending of 2.6, and then I'll check the other videos just to make sure it's still there. Okay, so I'm just adding the corresponding components. So I just lined them up one on top of each other and just added them up for question number 3. These are just unit quaternion norm. You know, these are just terminologies that we're trying to get used to on here. So I'm gonna put this aside for now. This is in the recording, so I'll post that later today so you guys can see and have these to check back on for your classwork for 2.7. I am going to start on rotations. All right, very exciting stuff. Here we get into the heart of it. So all this stuff was like preparation for what are quaternions and what are the math properties around them, but let's actually start using them to rotate. Okay. All right. So remember when we talked about things before, we said we had all these different angles, right? But what we want to do is we're in 3D. So this is rotations in 3D. So I've got my z-axis, my x-axis, and my y-axis, right? And what I'm going to do is I'll draw this into different colors so we can see it, is say I've got some kind of, we're going to do linear stuff. So I've got some kind of like a line, like a vector. It's like a line or a vector, you know, passing through. So I've got this line going through, right? And we're doing things that are linear, right? So we're passing through the origin. Remember our affine stuff. If this wasn't passing through the origin, we would bring our axis up so that we would pretend that our origin was now here at whatever our like, you know, offset was, do our rotations and then bring it back down. So the same thing would be true here too, but we're gonna do everything as though we're linear. So I've got this line U, my vector U, and I'm gonna go around that by some angle theta, okay? Now, picture it in your mind, right? I've got Z, X, and Y. I've got this line going through, and I'm going to go around this line by some degree. I'm going to go 30 degrees or 180 degrees or whatever around this line. Okay, I'm rotating around this line. So I'm rotating around this line. Now, quaternions, remember, I don't have to break up my angle, theta, my rotation angle, into X components, Y components, and Z components. I can just use this just one angle. I don't have to break it up into theta X, theta Y, and theta Z components, which is nice, right? Because remember how we said, well, that's computationally expensive, but it's also like we can run into problems. Remember how we can get this erroneous situation where I accidentally cancel out one of my degrees of freedom, and that would be bad. Okay, so let's say we've got a vector. We'll call it vector V. In our 3 dimensions is a quaternion whose scalar portion is 0. So it's going to look like I'm going to have 0 plus my vector V. So I'm forcing it into the shape of a quaternion, right? I'm adding that 4th dimension on it so I can do my quaternion stuff. So I've got my vector V. It's a 3-dimensional vector, has an X, Y, and a Z component. And now I'm saying I've got this, I'm adding this scalar portion, but I'm adding a 0. So we're kind of putting it into the quaternion shape, but we're not putting anything there, right? But it's going to allow us to do stuff. So when we do rotations using quaternions, we need our unit quaternion. Okay, and we're going to call, so we've got our quaternion if Q is equal to Q naught plus the vector portion. So we've got a scalar portion and a vector. So let's write that down in little colors here. So this is scalar and this is vector. Remember how we were just doing all of our quaternion stuff, right? And then basically, I'm going to be able to think about my unit quaternion. So I'm kind of rambling here, but just bear with me here. Let's try this. I'm going to do a little bit of derivation. Q squared equals 1, okay? Which basically means that my cosine squared of theta equals Q naught squared, and my sine squared of theta equals Q squared. Okay, I'm going to be using this because sine squared plus cosine squared equals 1. That's our Pythagorean identity. Okay, so I'm going to use that to help me put things together. But let me just talk about, this is our quaternion. Our conjugate of this is a subtraction. So it's going to look like Q equals Q naught minus. Okay. So I'll call that Q star. Okay. So now what's going to happen is this. We're going to put this together. Let's see. I'm trying to decide, like in our notes, we've got a lot of like stuff in here that talks about a lot of this thing. But basically, I'm going to skip some of the things in our notes so we can get right into the right into our rotation. So our unit quaternion. Okay, I'm going to be combining things with sines and cosines, and there's a reason that I'm doing it, but it's going to look like Q equals cosine of theta over 2 plus U bar sine of theta over 2. And then this U bar is a unit vector. Remember our unit vector, that's U bar over the magnitude of U. Okay, we need to have that be a unit vector. That's important. Okay, so this is the unit vector of the vector we are rotating around. So that was our U back at the beginning. So we're given a U. I need to convert that to a U, a unit vector. So I divide by its magnitude. Okay, so I get cosine of theta over 2 plus U, my unit vector, sine of theta over 2. Okay. So this is if we're rotating around this line that has U as a vector. Okay. I say it's a vector on the line, but remember how we always talked about it was a vector parallel to the line. Okay. Okay. So now to actually do the rotation in 3D, using quaternions, these are all like a preamble, using quaternions. Okay, what's going to happen? So we're going to say this is rotation of V about U by theta. Okay, so I basically have, right, I'm going to take, let's do this in green. So I've got my V, let's say I've got this, you know, V vector here. Oops, sorry, my V vector here. I'm going to take V and I'm going to rotate it theta degrees around this line with U on it. So let's call this, that's our line with our U vector on it. Okay, so to rotate V about U by theta degrees or radians, it doesn't matter. I'm going to say my rotation is equal to Q, which is a quaternion that we just talked about before, times V, which is our quaternion with 0 as its scalar, times Q star. And I'm going to tell you Q star is going to be our conjugate. I'll give you both Q and Q star. So our Q is equal to cosine of theta over 2 plus U, we'll call this over U, the magnitude, times the sine of theta over 2. That's our Q. Our Q star is equal to cosine of theta over 2 minus U divided by its magnitude, sine of theta over 2. It's the same thing, only I'm just subtracting. It's the conjugate, okay? And then we'll say V equals 0 plus V. So this is a quaternion also. So here, let me put this, I'm going to circle this in red. This is our rotation. And then the resulting answer is a vector that's been rotated in 3 dimensions. Okay, so all these 3 things put together are how I'm building up a rotation in 3 dimensions. We'll do examples so you can see. Okay, I'll let you guys finish writing that. Then I've got my lecture example page. So the first thing that we have is we want to rotate 1, 0, 1 around the line 1, 1, 1 by 90 degrees using quaternions. What are Q and Q star? This is example 4. So Q and Q star, that's what we're being asked for here. So Q and Q star, right? We're going to do these things here. So my theta is 90, okay? This is my U, and this is my V, okay? So my V becomes 0, 1, 0, 1, right? So this is my scalar portion, that's a 0, and this is my vector, my original vector. I need U divided by the magnitude of U. So this is going to be 1, 1, 1 divided by 1 squared plus 1 squared plus 1 squared, square rooted. So this is equal to 1 over a radical 3, 1 over a radical 3, 1 over a radical 3. Okay, that's my U divided by my magnitude of U. It's my unit vector U. Okay, so we're going to put these into our Q and our Q star equations. So Q is going to be cosine of 90 degrees divided by 2 plus my U over U magnitude, my unit vector, 1 over a radical 3, 1 over a radical 3 times sine of 90 over 2. Okay, my Q star is going to be the same thing, but subtract. So let's do this. Cosine of 90 over 2 is 45. Cosine of 90 over 2 is radical 2 over 2. Plus, this is 1 over radical 3, 1 over radical 3, 1 over radical 3 times the sine of, going to be radical 2 over 2 also. Sine of 45 degrees and cosine of 45 degrees are equal. Okay, so then this is equal to, see, I can make this radical 2 over 2 plus, this is actually equal to 1 over radical 2. So this is, I'm going to make this into 1 over radical 6, 1 over radical 6, 1 over radical 6. That's Q. And then my Q star is going to be the same thing, only subtracting. So it's going to be radical 2 over 2 minus. So these are the Q and the Q star that I need, and this is the V that I need. So I would be multiplying to do this rotation. I would do Q times V as a quaternion multiplication. I'd get a quaternion answer, and then I'd multiply that by Q star. It takes a long time to do this stuff. Okay. Alrighty. Let's go ahead and get started. We're going to rotate, okay? Okay, so we're going to rotate the vector 2, 1, 0. This is our V. Vector V equals 2, 1, 0. 180 degrees, this is our theta. Around the line R, 1, 1, 1, this is our U. Using quaternions, what's the new rotated vector? So I have to do 2 quaternion multiplications. This is why it takes a while. All right, so let's go ahead and get started. So let's think about, I need to come up with Q and Q star first off. So my Q is equal to cosine of theta over 2 plus U divided by the magnitude of U, sine of theta over 2. Let's fill in the blanks. Cosine of 180 divided by 2 plus, let's do this. This is U. This is 1, 1, 1 divided by 1 squared plus 1 squared plus 1 squared. We just did this, but I'll do it out again. Sine 180 divided by 2. Okay, so let's fill in the blanks. So 90 degrees. So cosine of 90 degrees is equal to 0 plus, we just did this, right? So this is going to be 1 over radical 3, 1 over radical 3, 1 over radical 3. Sine of 90 degrees is equal to 1. So my Q is equal to 1, Q is equal to 0 plus 1 over radical 3, 1 over radical 3, 1 over radical 3, okay? All right, so now my Q star cosine of theta over 2 minus divided by the magnitude sine theta over 2. That's a theta. So it's the same thing, but we'll just write it all the way out so you can see. I'm going to put a little circle around that. Okay, so cosine of 180 over 2 minus make sure you divide theta divided by 2 before you take the sine or the cosine of it. So this is cosine of 90, sine of 90. Okay, so cosine of 90 we said was 0. Sine of 90 we said was 1, so this is 0. I'm going to go like this, watch, plus, and I'm going to distribute that negative into all of those vector terms, minus 1 over radical 3, minus 1 over radical 3, minus 1 over radical 3. I find it easier to think of my quaternions as the scalar plus the vector, and then to incorporate that negative into all of my terms. This is Q star, so I'm going to put a little white circle around that. Okay. So I'm going to write down V as a quaternion equals, my V was 101, so that's going to be 0. I'm sorry, 210. 210. So as a quaternion, my V is equal to that. Okay. And now for the fun part. All right, this takes a while. So the first part, we're going to do Q times V. This is our first quaternion. So to do the quaternion rotation, we do Q, V, Q star. Okay, remember that. So I'm breaking this up into 2 pieces. My first quaternion multiplication is Q times V. So I'm going to start writing out. So Q, this is 0 plus. Don't worry about rationalizing this because you're going to have to do a whole bunch of math first. Do all the math first and then worry about it. Times my V. Remember, order matters. If it says Q times V, make sure Q comes first. Order matters because remember, we're doing a cross product in here. All right, so let's do these in the same color scheme. What did we do before? I did purple for the scalar part. All right. This is 0 plus. There. My scalar portion, I get 0 minus 2 over radical 3 plus 1 over radical 3 is 3. Minus times the minus gives me minus 3 over radical 3. Okay, so that's that part. I think we did the cross product in green. So then I'm going to do this, cross this. Okay, so it's going to look like I'm just going to keep the color scheme the same. Good. As it happens, these parts are both 0. Oh, I guess I could have done those in different colors, but I forgot. Okay, so now I'm going to add these two together, right? So now I get QV equals minus 3 over radical 3 plus okay, that's an intermediate step. I have to take this answer, right? This is my first part. And I have to multiply that by Q star. That's my second part, okay? Okay, so I'm going to continue that. I'm going to continue that on the next page. Okay, you guys all ready? I'm going to turn the page. Are you still writing? Probably going to be writing for a while. There's a lot of writing. Over here. So now our second step, part 2 is now we do second Quaternion multiplication. Okay, so the second Quaternion multiplication goes like this. We're going to take our answer from part 1, right? The Q times V that we just came up with, and we're going to multiply it by Q star. So that's going to look like minus 3 over radical 3 plus this is our answer for part 1 times our Q star, which was 0 plus negative, negative, negative. Okay. And I get to multiply. I get to do the same thing that I just did. And I'm going to keep working through. Okay, so let's go ahead and do it. So we're going to do our scalar portions first. So I'm going to go, I'm going to do the dot products. So this part is 0 minus. Okay. So remember, radical 3 times radical 3 gives me just a regular 3. So negative times negative gives me a positive. So this is 1/3. So minus 1 over radical 3 times minus 1 over radical 3 gives me positive 1/3. These two together, I think, oops, there's a radical 3. So 2 over radical 3 times minus 1 over radical 3 gives me a minus 2 over 3. Minus 1 over radical 3 times minus 1 over radical 3 gives me a 1 over 3. 1 over 3 plus 1 over 3 is 2/3. Minus 2/3 is 0. My scalar portion is 0, which makes sense because I'm taking a vector that's in 3 dimensions and I forced it into a quaternion by putting a 0 in its scalar portion, right? So I should get a 0 out here. All right, so 0 plus. Let's go ahead and do our cross products and our scalar multiplication. So I'm going to do cross product. So this is going to be cross. Cross. I guess we're going to go ahead and set that cross product up. All right. Okay, so I minus J. And plus K. Get really good at working with radicals. All right, equals I times minus 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 Okay, I'm just going to keep working through. Minus, minus, minus. And K. Minus times minus is positive. This is going to be minus times minus, that'll be plus. All right, a lot of writing. Okay, let's go ahead. So so 2, so this is 2/3 minus 1/3 minus J. This is 1/3 minus 1/3. 1/3 minus 1/3 plus K. This is 1/3 plus 2/3. Okay, so 2/3 minus 1/3. So I'm going to get oh, this should be, oh, sorry, I dropped the negative. There's a negative. Okay, so this is going to be minus 2/3 minus 1/3 is minus 3/3, which is a minus 1. This is a 0. This is 3/3, which is a 1. Okay, whew, that's the first one. All right, next one, I'm going to do Q0, this one times that one. So this is going to be minus 3 over radical 3 times, so this is my Q0 times, this is my scalar times my vector, minus 1 over radical 3, or radical 1 over radical 3, which is going to give me minus minus, that's going to be positive 3 over 3. This is going to be positive 3 over 3, positive, that's going to be 3 over 3. So this is 1, 1, 1. Okay. Next one, we're going to take this times that. Do that one in black. So then it's going to be 0 times this term right here. So minus 1/3, 2/3, minus 1/3. All radical. Which is going to give me 0, 0, 0. Okay, so now I get to add up all of these. So I'm going to go, let's do it all together. So my scalar is a 0 plus. Sorry, you can't see what I'm doing. 0 plus, let's add up these pieces here. Minus 1, 0, 1. Plus 1, 1, 1. Plus 0, 0, 0. Okay. Whew, almost there. So let's put it all together. So I'm going to get 0 plus minus 1 plus 1 is a 0. 0 plus 1 is a 1. 1 plus 1 is a 2. Okay, which gives us, so we rotated vector. Let's write down what was our original vector. Our original vector was 2, 1, 0 by 180 degrees around 1, 1, 1. Okay, and then we're going to get 0, 1, 2. Okay, so it's going to look, let's draw out a picture. Let's see if we can visualize. Here's my axis. Here's my X. Here's my Y. Here's my Z. All right, let's go ahead and see. So we're going to rotate that around 1, 1. So I go over 1, go over 1. I'm going to go up 1. So it actually comes up off the page. How am I going to draw that? I'll draw that over to here. So this is like, okay, we're rotating, and we're rotating 180 degrees around that, right? So, and I'm going to take the vector 0, 1, 2. So I go 0 in the X, 1 in the Y, and then 2 in the Z. So 0, 1, 2. So I'm going here. And I'm going to rotate that 180 degrees. Around this thing here. And then I'm going to get, as a result, 0, 1, 2. So 0, whoops, I did that wrong. That's my answer. Rotated 2, 1, 0. Sorry, I'll draw it this way. 2, 1, 0. And I'm rotating that 180 degrees around, and I'm going to end up there. So I start, I rotate it around this thing here, and I end up at that spot. Okay. Phew. That's a lot, right? But we can do it. Okay, guys.
I have a question.
What's up?
So what happens if the scalar is not 0, if it's 1 or 2 or something?
Yeah, so the scalar should end up being 0 because we're taking a 3-dimensional vector and we're rotating it in 3 dimensions, right? So your scalar, this part here should end up being 0. If it ends up being something other than 0, then now you're in 4th dimensions and it's kind of like an offset. It doesn't quite work. So you need to it should come out to be 0. Because remember, we took our vector, our input vector, and then we converted our input vector into a 4-dimensional thing by adding that 0 component into its scalar place. So yeah, it's a great question, but no, it should come out to be 0 because we're looking for our vector at the end.
Okay, thank you.
Yeah, sure. Okay, guys, I will scan this in and upload it later today. And then so that you guys can have all of this stuff, maybe you can see the colors a little bit better too. And then you can kind of have it for when you're doing it. When we meet again, we'll go through some practice problems, rotations using quaternions. We'll do our classwork page, and then we'll start on part 2, which is rotations not using quaternions. And it'll look like, oh, isn't this nice? But it's actually computationally more expensive because we're doing like cosines and sines and matrix multiplications. Okay, whereas here we're just doing vector multiplications, cross product and scalar. So it's computationally much cheaper. Okay, all right, guys. Hey, have a great day, and take it easy. Okay, bye.
Thank you.
Take care. And I do have office hours today.
Okay, that was a lot.
I know, right? Your brain's probably full, right? I need to take a break. Take a break, go out for a walk, have lunch, think about it. There's a lot of stuff that you have to sift through, and then I'll post all the videos so that you can have the examples and you can slow it down and then pause it and stuff like that and make sure you have it. And I'll scan this in so that you can have the actual math actually written down too.
Okay, thank you.
Take it easy.
All right, you too.
Bye.